Hello and welcome to Engineer's Mindset. So in today's video, we are going to be looking at electric force and Coulomb's law. The first part of the video, I'm going to be showing you everything you need to know about Coulomb's law and all the mathematical equations that are involved. Whereas in the second part of the video, we are going to be picking some problems to explain everything we learned in the first part of the video. So do well to watch the video to the end, because I'm sure you don't want to miss any part of the video. Alright, so sit tight while we begin the class. Welcome back. So let's say that we have 2-point charges. We have a positive charge and we have a negative charge. Let the positive charge be Q1 and let the negative charge be Q2, and let the distance separating these two charges be R. Okay, now since these charges are opposite in signs, this is positive and this is negative, and they are placed in an electric field, this charge Q1 will experience a net force that will pull it or cause it to move in the direction of charge Q2, whereas charge Q2 will also experience the same net force that will cause it to move in the direction of charge Q1. These two forces are equal but opposite in direction. Now let's imagine that we have two equal charges also placed together in an electric field. This is positively charged, this is also positively charged. Let this charge be Q1 and let this charge be Q2. Once more, distance apart, let this distance be R. Now since these charges have the same signs, charge Q1 will experience a net force that will compel it to move opposite the direction of charge Q2. So we'll have this to be F. Charge Q2 will also have a net force which will cause it to move against the direction of charge Q1. Now this is simply because these charges are the same. Now what is the idea of the Coulomb's law considering 2-point charges placed in an electric field? The Coulomb's law simply states that the force of attraction between these 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of their distance apart. So two key things you pay attention in that definition. One, the force is directly proportional to the product of the charges. So let's put that down. We have that the force is directly proportional to charge Q1 multiplying charge Q2. That's the first equation as picked out from that law. The second part of the law says the same force is inversely proportional to the square of their distance apart. So this means that force is inverse simply means reciprocal, and the distance as chosen here, distance is simply R. So inversely proportional to the square of the distance. So all over, or 1 divides R squared. Call this equation 2. Now if you join these two equations together, you're simply going to obtain that this force, since the two forces are the same, this force is directly proportional, remember, to the product of the charges Q1 multiplying Q2, and then inversely proportional to the square of their distance apart. You have this. Now if you take away this proportionality sign, you already know whenever we take away a proportionality sign, we always introduce a constant. So this simply implies that force is equal to K Q1 Q2 all over R squared. Okay, where K is called constant. Okay, and the value of this constant K is given simply as 9 by 10 to the power of 9 newtons meter squared per coulomb squared. K can also be expressed as a function of permittivity. Okay, K also can be expressed simply as 1 all over 4 pi epsilon naught, where epsilon naught is the permittivity of free space and it has a value. The epsilon naught, okay, has a value of 8.85 by 10 to the power of negative 12 coulomb squared per Newton meter squared. Okay, So that's the value of the permittivity of free space, also called epsilon naught. Now, there are some important things we need to learn about the Coulomb's force of attraction. Okay, so we're given that force is simply equal to kq1 q2 all over r squared. Let's consider that q1 is equal to 1 coulombs, q2 is equal to 1 coulombs, and the distance of separation and r is equal to 1 meters. Let's see what we are going to obtain for the force. This simply implies that force is going to be equal to, remember we said let k be 9 by 10 to the power of 9. Obviously that's the value for k, okay, multiplied by, now we are calling q1 and q2 1, so that means multiply by 1, multiply by 1, divide also by r squared, and r is 1, so divide simply by 1 all squared. Now this simply means 9 by 10 to the power of 9 multiplies 1 remains 9 by 10 to the power of 9 all over 1 squared is 1. So this simply implies that the Coulomb's force F has a value of 9 by 10 to the power of 9 newtons. Remember, force is always measured in newtons. Now, what happens when I double one of the charges? Now, let's say, let us double one of the charges. Let q1 be equal to 2 coulombs, and let q2 still remains as 1 coulomb, and let the distance r still remains as 1 meters. If we plug these values into the equation, we are going to have our force of attraction to be equal to, remember k stands for 9 by 10 to the power of 9 multiplied by, now we'll change q1 to be 2 coulombs, so you have times 2 times q2 is 1 divided by, distance remains unchanged, which is still 1 all squared. Now this simply implies that our force of attraction is going to be approximately 18 by 10 to the power of 9 newtons. Okay, so you observe that when we doubled the charges, when we doubled one of the charges, the value of the force increased. In the first instance, when the charges were 1 1, we had this to be the value of the force, 9 by 10 to the power of 9. But when we doubled one of the charge, the force increased. Now let's keep these charges q1 and q2 to be 1 coulombs, then let us increase the distance and see what happens. Now if we increase the distance, okay, I can take this off now. Now if you increase the distance, so you're simply saying let r be equal to 2 meters. Now we are keeping q1 as 1 coulombs, and you're keeping q2 also as 1 coulombs. So from the force of attraction, you simply have, remember k is 9 by 10 to the power of 9, q1 is 1, q2 is 1 all over r squared. Now r is 2, so you have 2 squared. Now this is going to be equal to 9 by 10 to the power of 9 multiply 1 remains 9 by 10 to the power of 9 divided by 2 squared gives us simply 4. So this simply implies that our force of attraction between those 2 point charge becomes 9 by 10 to the power of 9 divided by 4. Let us obtain this value and see. That gives us 2.25 by 10 to the power of 9 newtons. Okay, so this becomes our force when the distance is increased. Now what does this tell us? If you observe, when the charges were 1 and 1 and the distance apart was also 1, we obtain our force to be 9 by 10 to the power of 9. When we kept the distance and increased one of the charges, the value of the force increases to 18 by 10 to the power of 9. Now when we kept the charges as 1 and 1, then increase the distance, what happens is that the value of the force decreases. So this simply tells you that when charges are placed very far apart in an electric field, their value, or the value of the force of attraction between them, drops. So if I have 2 point charges, this is positive charge, and I have another point charge negatively charged. Now this is q1 and this is q2, now separated by a very small distance. The force of attraction between these 2 charges will be larger than when I have or when I separate the distance between these two charges by a much larger value. So this is positive and this is negative. Now I have my Q2, I have my Q1. Okay, so when the distance between them, distance of separation between them is increased, the force of attraction between them is reduced. But when the charges is increased, the force of attraction between them is increased. Now this simply tells us that in order for us to increase the force of attraction between 2 point charges placed in an electric field, there are two conditions that must be met. The first condition is either you're leaving the distance the way it is and increasing the charges. That helps to increase the force of attraction between the charges. Or you're keeping the charges and reducing the distance between them. The closer the charges are together to themselves, the higher the force of attraction between them. Now I'm going to use an example now to explain that. Let's say that this distance is no longer 1 meter. Let's keep the charge as 1 coulomb, the two charges as 1 coulomb and 1 coulomb. Now let us reduce the distance between them from 1 to 0.5. Let's see what we are going to obtain. Okay, I can take this off now. So you observe that when R is reduced to 0.5 meter, okay, and Q1 still remains 1 coulomb, Q2 still remains 1 coulomb. Let's see what happens to the force of attraction. Force is equal to, we said K, and K is 9 by 10 to the power of 9 multiplies Q1, which is 1 coulomb, multiply Q2, also 1 coulomb, divide by distance separating them all squared. And distance now has been reduced to what? 0.5. So we have 0.5 all squared. Let's see what this value is going to give us. 9 by 10 to the power of 9 multiplies 1 here, remains 9 by 10 to the power of 9 all over 0.5 squared will simply give us 0.25. Now let's obtain the value of the force of attraction. Now 9 by 10 to the power of 9 divides 0.25 simply gives us 36 by 10 to the power of 9 Newton. So you see that when the distance or separation between the 2 point charge in the electric field was reduced, the force automatically increases. So two conditions that needs to be satisfied if at all you want the force of attraction between 2 point charges to increase. It's either you're keeping their distance the same way it is and increasing one of the charges, or you're keeping the charges and reducing the distance. The closer the charges are to themselves, the higher the force of attraction between them. Alright, so always keep it in mind that the force of attraction between 2 point charges is given as KQ1 Q2 all over R squared. So it is important for you to know that this force is actually a vector quantity, and since it's a vector quantity, it means it has magnitude and direction. Now when you're solving the problem or you're solving any given problem with this helps you to find the magnitude of the force. But if you're solving in terms of vectors, then the force in terms of vectors, the force of attraction between 2 point charges is simply given as K Q1 Q2 all over the magnitude of the position vector between charge 1 and charge 2 all squared multiplied by the unit vectors. And what is this unit vectors? The position vector between the two charges, which is R1 minus R2, okay, divide by the magnitude of the position vector between charge 1 and charge 2. So this becomes your unit vector. So in vectors form, this is how you tackle your problem. So all you need to do is find the position vector between the two charges in the electric field, find their magnitude. When you divide these two together, you obtain what is called the unit vectors. Now use these unit vectors to multiply by this component. It gives you the value of the force in vectors form. So we are going to be coming to that in much later videos that we are going to be doing. So I'm sure you want to be a part of that video. Do well to hit the subscribe button at this point in time and turn on your notification bell so that you get updates when that video drops. Okay, so let's continue. So this is how to find the magnitude of force of two charges in electric field, and this is how to find the force of the two charges in electric field in vectors form. Now we are going to be applying the knowledge of charges into the nucleus of an atom and see what we can learn from there. All right, welcome back. Now let's apply electric charges to the nucleus of an atom and investigate to see what that looks like. Usually, we know that atoms are spherical in shape. We know that all atoms are spherical in shape, and in the center of the atom lies what is called the proton, P, and the neutron, N. Okay, whereas we have electrons revolving around the atoms. We have electrons revolving around the atom, E. Now, one proton charge is given simply as 1.6 by 10 to the power of negative 19 Coulomb. One proton charge is given as 1.6 by 10 to the power of negative 19 coulombs, whereas one electron charge is actually what? The same in magnitude as the proton charge, but opposite in direction or opposite in charges. So one electron charge is simply given as negative 1.6 by 10 to the power of negative 19 Coulomb. Now, if you see an object that is positively charged, it simply means that that object has more protons than electrons. But if you see an object that is negatively charged, it simply means that object has more electrons than protons. But if you see an object that is neutral, that simply means the object has equal protons as well as it has equal electrons. So it means that the electrons and the protons of that particular object are what? The same. Now, keeping this in mind, let's now move to all the vital units for the given Coulomb's force of attraction. Now, usually we know that force is measured always in Newton. So the Coulomb's force is measured in Newton. The charges itself are measured in coulombs, C. Whereas the constant of proportionality is measured in Newton meter squared per coulomb squared. Now, your distance arrow is measured in meters. Sometimes the distance can be measured in centimeter. It can also be measured in millimeter. So always be sure to know that 1 centimeter is equal to 10 to the power of negative 2 in meters. When the distance is given to you in centimeter, it is usually wise to convert it to grand units. That is simply converting into meter. Sometimes the distance can also be given in millimeters. So keep it in mind, 1 millimeter is simply going to be 10 to the power of negative 3 in meters. Sometimes the charges can also be expressed in microcoulombs or millicoulombs. When the charge is in microcoulombs, 1 microcoulomb is simply equal to 10 to the power of negative 6 coulombs. And when the charge is in millicoulombs, it's important to know that 1 millicoulomb is simply equal to 10 to the power of negative 3 in coulombs. So these are the few dimensions that you need to keep in mind, or these are the few units pertaining to everything we've learned that you need to keep in mind. Alright, so that's the end of the first segment of the video. As promised earlier, in the second segment, we are going to pick up a little example to express or back up everything we've learned in this first segment. I'm sure you want to be a part of it, so do not skip in a hurry. Sit tight while we begin the second segment. Welcome back. So let's consider this question on the board to explain everything we've learned in the first segment of the video. Now the question says 2 point charges of magnitude 3 microcoulombs and 5 microcoulombs are placed in electric field as shown below. Calculate the magnitude of the force of attraction between them. So you're given the first charge Q1 was given simply as 3 microcoulombs. Now, not forgetting, convert your microcoulombs to coulombs, and 1 microcoulomb is 10 to the power of negative 6. That means 3 microcoulombs becomes 3 by 10 to the power of negative 6 in coulombs. Second charge Q2 was given simply as 5 microcoulombs, and this is equal to, this becomes 5 by 10 to the power of negative 6 coulombs. Now, distance of separation between the two of them is simply 2 meters, as can be seen. So this simply implies arrow is given as 2 meters. Now we need to find the force of attraction between these 2 point charges. Recall your formula. Force, okay, is simply equal to K Q1 Q2 all over R all squared. So this is going to be equal to What is our K? Our constant, remember, is always 9 by 10 to the power of 9 multiplied by, now the first charge, we obtain the first charge as 3 by 10 to the power of negative 6. So you have 3 by 10 to the power of negative 6 multiplied by the second charge was given in the equation as 5 by 10 to the power of negative 6. Okay, the whole of this divided by the square of the distance, and distance is 2 all squared. So this means that the force of attraction between the two charges becomes, let's obtain or let's multiply everything at the numerator. So do well to point along with me to avoid any calculation errors. Okay, so everything at the numerator gives us 0.135 divided by 2 squared is 4, and this is going to be equal to, let's divide this value by 4. We have approximately 0.83 newtons. So the force of attraction between them is simply 0.83 newtons. Now, the reason why this force of attraction seems to be quite small is simply because of the charges. The charges has a smaller value, and remember when I said earlier that if you reduce the value of the charge and increase the distance, the magnitude of the force will drop. But if you reduce the distance and increase the charges, the magnitude of the force will increase. Alright, so these charges here are quite small. 3 microcoulombs and 5 microcoulombs are very small values, which is why it actually dropped the value of the force of attraction between them. So that's it for this video. In the next video, I'm going to be applying the Coulomb's law in vectors form. I'm sure you want to be a part of that video, so do well to hit the subscribe button and turn on your notification bell so that you don't miss out on that video when it drops. I hope to see you in that video. Please do well to appreciate my work by liking this video, commenting nicely, sharing to your friends, and if you're new to the channel, do well to subscribe as well and turn on your notification bell. I will see you in the next video. Cheers.